Have you ever played with magnets? That invisible push and pull, it feels like pure magic, right? But what if I told you it's not magic, but some of the most fascinating science in the universe? Today, we're going to demystify magnets and find out exactly what makes them tick. Stick around, because by the end of this, you'll see the world in a whole new magnetic way. So, let's start small. Really small. Like, atom small. Everything around us, from the chair you're sitting on to the air you're breathing, is made of atoms. And inside these atoms are even tinier particles called electrons. Now, here's the key: electrons are constantly spinning. Think of them as microscopic spinning tops. This spinning motion creates a tiny, and I mean really tiny, magnetic field. So, in a way, every single atom is a potential mini-magnet. You might be thinking, well, if everything is made of atoms with magnetic electrons, why isn't everything magnetic? Why doesn't my wooden desk stick to my metal lamp? That is a brilliant question. The reason is that in most materials, these little electron spins are all jumbled up. They're pointing in every random direction imaginable. Imagine a massive crowd of people all pointing in different directions. The overall effect: chaos. They cancel each other out. There's no single, unified direction, so there's no overall magnetic force. Your desk, your clothes, even you, were all non-magnetic because our atomic magnets are a disorganized mess. But in some special materials, something amazing can happen. These are what we call ferromagnetic materials. The most famous ones are iron, nickel, and cobalt. In these materials, the atoms can get together and decide to point their magnetic fields in the same direction. It's like that chaotic crowd suddenly getting organized and everyone pointing forward. When millions and billions of these atoms align, their tiny magnetic fields add up, creating a larger, stronger magnetic field. We call these organized groups magnetic domains. Now, a regular piece of iron isn't automatically a magnet, even in iron. These domains can be pointing in random directions, canceling each other out. It's like having several organized groups in a crowd, but each group is pointing a different way. The net effect is still zero. So how do we turn that piece of iron into the magnet you can stick on your fridge? We need to get all those domains to line up. This is where a strong external magnetic field comes in. When you bring a powerful magnet near a piece of iron, its magnetic force acts like a drill sergeant, shouting at all those little domains to get in line. The domains that are already pointing in the right direction grow larger, while the ones pointing the wrong way shrink and flip around to align with the external field. Once enough of these domains are pointing in the same direction, voila! The piece of iron has become a magnet. Its north poles are all facing one way, and its south poles are all facing the other. This explains the two types of magnets you might have heard of: permanent magnets and temporary magnets. In a material like soft iron, the domains line up easily when a magnet is nearby, but as soon as you take the magnet away, they go back to their random, jumbled state. It was only a temporary magnet. But in materials like hardened steel or special alloys like neodymium magnets, the domains are a bit more stubborn. Once you force them to align, they tend to stay that way even after the external field is gone. This creates a permanent magnet, the kind you buy in a store. So we have our magnet, with all its domains lined up. What's next? This alignment creates an invisible field of energy that flows out from the North Pole and loops around back into the South Pole. This is the magnetic field. You can't see it, but you can definitely see its effects. The classic experiment is to sprinkle iron filings on a piece of paper with a magnet underneath. The filings will magically arrange themselves along these invisible lines of force, giving you a beautiful map of the magnetic field. And this field is what causes the famous attraction and repulsion. When you bring the north pole of one magnet near the south pole of another, their field lines link up. They want to connect, pulling the magnets together. It's like they complete each other. But if you try to push two north poles together, their field lines push against each other. They're flowing in opposite directions and can't connect, so they repel. This is where the rule opposites attract and likes repel comes from. It's all about how these Invisible fields interact. What's truly mind-blowing is how deeply connected magnetism is too. Another fundamental force, electricity. In the 19th century, scientists discovered that a moving electric charge, basically an electric current, creates a magnetic field. This is the principle behind electromagnets. You just wrap a wire around an iron core and run electricity through it. The current creates a magnetic field, which then aligns all the domains in the iron core, making it a very strong, but controllable, magnet. Turn the power off, and the magnetism disappears. This is super useful in everything from junkyard cranes that pick up cars to the complex machinery in MRI scanners. And the connection goes both ways. Just as electricity can create magnetism, magnetism can create electricity. If you move a magnet near a coil of wire, it will push the electrons in the wire and make them move. Moving electrons are what we call an electric current. This principle, known as electromagnetic induction, is the foundation of our modern world. Almost all the electricity we use is generated this way, by spinning massive magnets inside coils of wire in power plants, whether they're powered by wind, water, or steam. So, from the tiniest spin of an electron to the giant generators that power our cities, magnetism is an invisible force that shapes our entire world. It's not magic, but it's a fundamental property of our universe, born from the motion of charges. Even our own planet Earth is a giant magnet. Its molten iron core acts like a huge dynamo, generating a massive magnetic field called the magnetosphere. This field extends far out into space and protects us from harmful solar radiation. It's also what makes a compass needle point north, guiding explorers for centuries. The next time you snap a magnet onto your fridge, take a moment to appreciate the incredible physics at play. You're holding a piece of material where trillions upon trillions of atoms have decided to work together, creating a unified force that can reach out and interact with the world. You're witnessing the organized dance of electrons, a fundamental force of nature, right in the palm of your hand. It's a beautiful reminder that even in the most ordinary objects, there's a universe of extraordinary science waiting to be discovered. Thanks for joining me on this magnetic journey today. If you found this as cool as I do, make sure to hit that like button and subscribe for more deep dives into the science that surrounds us. Got any questions or ideas for another topic? Drop them in the comments below. See you next time.